Welcome, everybody. This is our next episode of the Programming Principles series we have here in Hotovo. And this time we're going to be talking about generics, and we're going to explore more of a deeper level of generics beyond basic usage. So the last time I talked a lot about polymorphism, like what kinds of polymorphisms we have, how do we use them, and how they're implemented in various languages. So this time we're going to be talking about generics, which is one type of polymorphism, more specifically parametric polymorphism, but they can as well be used to implement ad hoc polymorphisms. So what's the definition of generics? In a simpler terms, they are implemented as functions and classes that abstract from concrete types. So they don't use specific types like strings, numbers, objects, interfaces, and so on, but a generic type or an abstract type, which can be any type. The motivation is to reduce code duplication. So instead of having implementation, for example, for lists, for a list of strings, list of numbers, list of objects, we may have just a one list implementation that can operate on any type of object. It's important to say that usually the generics are implemented only at the compiler level, but there are some exceptions to that. I'll explain that later. But generics are removed when during runtime. Now I'm talking specifically about JVM languages, and compiler handles checks the correctness of the code, including the generics. But when it gets compiled, it's removed. This is called erasure or type erasure. And most common usage for containers, is for some kind of containers like collections or options, wrappers. So these are types that don't care what they contain or what they wrap. They just care about some operations on those objects, but they don't care about what types these are. So here we have oversimplified example of a class option that uses a type parameter t, and it can contain the value of type t, and it can return the value of type t. So it really doesn't care what the t is. It might be, as I said, string, number, an object, whatever what can be captured and held on heap or in memory. So this is very basic example. Now, I think that everybody from the junior level programmers understand that there are generics in that sense, but we're going to explore a bit more about them. So I'm going to be using these languages as for examples, and we can see how they are the same in terms of language syntax and when they differ and what kind of features about generics they support. So it's quite interesting that, for example, when we declare a class, a generic class, here in this example, it's list, and the type parameter is in angle brackets. The declaration is same in Java, Kotlin, and Typescript even. Scala decided to use square brackets instead of angle brackets. And Rust uses square brackets, but it doesn't have classes, but it has structs anyway. So once you're familiar with generics in one language, in terms of class declaration, it's mostly the same in the rest. How, as I mentioned before, the generics apply to the classes or interfaces and functions or methods. If the function is within an object, it's a method. So in Java, we declare the type parameter t up front, and then we can use it in either the return type or the parameter type. Kotlin uses the same approach. You just need to declare a function as a fun, and the type goes after the name of the parameter. Similar with Scala, instead of fun uses a def keyword, and the type parameter goes after the name of the function. So in Rust, similar, is not fun, but it's fn this time. And we have a TypeScript syntax here, which is similar to Rust one. So you can take like throw all of the combinations in a box, pull out something, and you would get like a new syntax for a new language. So this presentation is going to be mainly about variance, because this is one of the concepts in generics that is not well understood. So we'll try, I'm going to try to explain that a bit more. So what does variance mean? Imagine we have like a hierarchy of classes or types. So let's say a B is a subtype of A. Now, variance tells us what happens if we have a generic type C, which can hold the type parameter, and if that type parameter is within that hierarchy, what it happens with the generic type C. So invariance means that if B is a subtype of A, there's no relation between type C with the generic type B and type C with generic type A. For like easier understanding, let's use like imagine a list, for example. So if we have a list of B, invariance means that there's no relation to the list of C in terms of inheritance. Covariance means that if B is a subtype of A, then a list of B might be a subtype of list of A. Now, why is that important? Is because when we have like the basic subtype polymorphism, we can assign a list of B to a list of A, or we can pass to a function which accepts a list of A. We can pass in a list of B. Now, we'll have some examples about that. Now, contravariance is even more difficult to understand, because it's not easy to imagine like how this could work. But it's simply the other way around. So if you have a list of A, then a list of A is a subtype of list of B. Now let's look at Java implementation. So Java uses something called call site, or sometimes referred to as a use site variance. What this means is that the variance is defined when it's used, not when it's declared. It uses wildcards and type bounds to implement the variance. So in this example here, we have a person class and we have a worker class, which extends person. So based on the picture I had before, now we'll create a list of workers. Here we have a list of workers, and we may have a list of persons. But in Java, lists are not covariant. So this line doesn't compile. The compiler would reject that, because we can't assign a list of workers to a list of persons. Because even though a worker extends from a person, list of workers doesn't extend from a list of persons. Now, the reason is that I'll show an example like in Typescript where the compiler allows that and it blows up on runtime. Java doesn't compile, which is correct, because lists are invariant. Now, what we can do, this is actually a call site variance. So we tell that we have a list of something that extends person. And now we can happily assign it a list of workers. However, what we can do with list of persons? Not much. Because we can't add to it anything. We can only get from it. Because if we get something which extends person. So we can't work with worker fields or worker methods, but we can work with person methods. So this list is covariant to this list. Why this is necessary or can be used, I'll show you in a bit. Now, on the other way around, if we have a list of persons here, we can assign it to a list of something that is a super type of worker. So this is a contravariance. Now, this is not really useful because if something is a super type of worker and we don't know what that might be, all we can work with is an object, right? Because object is a super type of everything, of all classes. For correctness, I'm not talking about like primitive types. So we're always in the land of objects and classes. Now, Scala uses something called declaration site variance. And how this looks like. So we have the same hierarchy of objects, but now the type parameter can be denoted with the plus sign or minus sign. So the plus sign here means that the type A is covariant. So now if we have a list L1, which is list of workers, Scala allows to assign it to a list of persons. Now this assignment doesn't make much sense, but you can think of it when I'm passing something to a function, right? So this is more like a realistic example. And this is just for demonstration. Because a worker is a subtype of A and the list is covariant on type A, I can assign a list of workers to a list of persons. Now, why this works is because lists in Scala are immutable. So we can't add to it. If we could, like in Java, I could add a person, not a worker, a person, to a list of persons, but it's the same well, L1 and L2 refer to the same object list, which is a list. So if I added a person here, L1 would contain a person. But since L1 is a list of workers, I would assume that I can get back a worker and call worker methods and worker fields. But it would blow up because I added a person to that list. But list is immutable. I can't add to it. Then it's perfectly fine. Now, this is an example how Scala compiler complains that if we are trying to use covariance and contravariance on a generic type, but here the var means that the value is mutable. But if I was able to mutate it, I would break that covariant law. So the compiler doesn't allow it. Same with the contravariant thing. Now, how these languages implement the declaration site variance. So as I showed you, there's no declaration site variance for Java. Kotlin has it. It has a special syntax or keywords out and in. And these are really I think well thought because they immediately mean something that when I consume something, I'm passing something in, then it's contravariant. And when I'm reading something or I'm holding something, then it's a way out. So in Scala, it's plus and minus. In Rust, this is automatic based on mutability. Again, Rust has like by default immutable references, but when they are marked as mutable, it has an effect on the variance. So if a field is mutable, then it can't be covariant. If it's immutable, it might be covariant. And in TypeScript, this is quite interesting because TypeScript, due to the structural typing mechanism, is a bit different, but it doesn't support like declaration side variance, but it has some rules for functions only. So there is a compiler parameter that I can enable or disable called struct function types. And when it's enabled, it understands that when I'm assigning a function to another, to reference to another function, or passing function as an argument, it has to follow those rules. And the rules for function is, and it's my favorite line, that function is contravariant on its input parameters and covariant on the return type. And I'll explain that. So this is the example that I mentioned, like when it goes wrong, when the type system is not sound, it may leak. So this is a TypeScript example. We have a simple class wrapper which accepts a type parameter t. Now I can construct a new wrapper with any type. Let's have an animal and a dog hierarchy. Now I create a new wrapper of dog. So I can pass in dog. So W1 is a wrapper of dog. Now, due to the lack of variance or contravariant or covariance, I can create a wrapper, or actually create a type of wrapper of animal and assign it wrapper of dog. So far, so good. Now I can add, or I can replace the value with the new animal. But mind that W1 and WT are references to the same object. So if I take a W1 value, W1 is wrapper of dog. I pull out the value, it's a dog, but it's really not a dog, it's an animal. And here the TypeScript compiler can't see a problem. But if I run this example, it fails in runtime, it throws. So some more examples where these are used, like what's the real usage of covariant generics and contravariant generics. In Java land, there's a simple mnemonic definition that producer extends and consumers super, which means that if I have a covariant generic, it's producer, so I can get the type of it out of it, but I can modify it. On the other hand, if I have a consumer, so something that accepts a type, then it's a contravariant. So as I said, covariance is used in immutable containers and contravariance in consumer functions. And this is the line that I mentioned, that the function is contravariant in input type and covariant in return type. So out from the SDK, Java SDK, this is not like made up example. It's a real interface, Java interface list. And we see here that Java doesn't have like declaration side variance. However, we have methods on a list like @all, which can accept not only collection of E, but a collection of anything that extends E, because one by one we copy those elements to the list, and we can get out from the list those elements, but only as references to type E, not something that extends E. So this is covariance. And contravariance The most common usage is like for sorting, comparators, comparables, and so on. We have a method sort here that accepts. So we want to sort the elements of the list in some way, and in what way tells us the comparator implementation. However, it doesn't have to be like just the comparator of types E. It may be any type that is a supertype of E. Now, why this works? Like, think hard, because this is hard to process. I understand that. If I call the comparator with elements of E, and the comparator can understand anything that it's supertype of E, it can handle that. Because it calls methods and fields of types that are supertypes of E. Right, so next, let's move to Scala. Again, this is like a function definition. Every time you write down like this kind of a fat arrow syntax or lambda function, it just transforms to this type, function T. Now, the input type with the minus sign is contravariant, and the return type is covariant because it's the plus sign, which means that to this function, I can assign a different function that can accept a supertype of T, and it can return a subtype of R. Next example is from Kotlin list. Again, this is like standard library in Kotlin. And in Kotlin, the lists are again immutable, and they can declare the type as covariant. One more contravariance example. I borrowed this from a great presentation from a YouTube channel called Rock the JVM. It's mostly for Scala language, but I find this example really great. So we have a class animal and we have a class dog, which extends animal. Now let's have a animal doctor, veterinary, vet, which can heal an animal of type T. And this is just an interface. Let's have an animal that implements vet with the type animal. So it can heal any animal. Now we want to treat our dog. Our dog is sick. And you can take the dog to a dog veterinary, which would be super because, of course, dog vet can treat dogs the best. However, if we don't have like a dog veterinary around, any veterinary would suffice, right? So we have this function here that accepts a vet, an animal doctor, and our dog. And this should be a dog. Since the vet here is declared with the contravariant type dog T, this means that I can provide any vet which can treat any animals, like I'm doing here. So this is the call site variance in Java. So I pass in an animal vet which accepts dog. If we didn't have this here, this question mark super, if it was just like a vet of dog, this would not compile. I wouldn't be able to pass in an animal vet because, as I said, in Java, the classes or the type parameters are not variant, so the compiler would not allow it. But in this way, it's okay. All right, enough of the variants. Let's talk about different generic features and how those languages implement them. So defaults, this is a really simple concept. So we may have a generic type accepting a type T or type parameter T, and I may assign it a default value. So if I don't provide the type when I'm using the generic type, it would default to something. So this is supported by Rust and TypeScript. And this is quite common in React code base, for example. Bounds. So those generic types may have bounds or type bounds. So Java in a call side supports both extends and super. Kotlin implements that type bound like here. So type T can be any subtype of a person. Lover bounds are not available. But again, as Kotlin supports declaration side variants with in and out keywords, it can easily assign that. Scala supports type bounds in this form. Rust, similar to Kotlin, doesn't support lover bounds because it's usually needed. TypeScript, same. Now, intersections are like algebraic data types that they're composed of two types. So for generics, we can define like a type T, which may be both a reader and a writer in this example. So it may extend a reader and a writer. So even though like intersection types are not available in Java, in generic types, for generic types, they are available intersections. Kotlin supported with the var keyword, where I can define multiple constraints for the type T. Scala, same thing with this syntax. Rust supports it with the plus sign here. And of course, TypeScript supports intersection types at the basic level. So it also supports it on generic types. And reification, you might have heard this term. And reification means if we're bringing back something abstract to something more concrete. So as I said at the beginning, generic types are erased. So during runtime, the JVM doesn't know that there were like a type T. There was some type T or some generic types. It's all just one implementation using objects. With an example, this is I think quite common misconceptions that Java doesn't understand generic types at all on runtime. But I have an example where I'm showing that this is not true. Now Kotlin can reify type T with inline functions. Inline function means that there isn't a call to function on runtime, but the compiler replaces the invocation of the function with the function body. This is inlining. And if we have an inline function, then we may tell the compiler to reify the T. And this means that at runtime, I can get the class of T, which I can't in Java, because it's all objects at runtime. I can't get the class of T. But here, Kotlin supports it, and I can get the class of T and for example, create new instances of T, which isn't possible with Java. Scala has like a handlebar, like special type tags. If I pass in the type tag to a function, then it can hold that information about the type T. Rust does support reification because it's actually doing what's generic trying to avoid, and this is, it would actually produce implementation for each type that it's called with. So if we have a function that it's called with string and a number, it would actually produce two different implementations due to the needs of Rust to have like exact memory semantics of a function. And TypeScript doesn't support reification. There's no information about types at runtime, but it's achievable with compiler plugin. And the last thing, that reification, what I was talking about in Java, it's really about if I'm passing an object of type T, it's on just an object. However, the type erasure doesn't apply to like class metadata. So this is an example where I have a class myComparator and it implements a comparator string. Now, using like reflection methods, on runtime, I can get the type of this thing here, because this is like a class declaration and it's stored within the class metadata. So it's available on runtime. So using generic interfaces method here, I could get the comparator interface. I cast it to parameterized type, and I can get the actual type arguments, which is, so this would print out a class, like a string class. And this was everything I had for today. So thank you very much. If there are any questions, I'm happy to answer them now.
Actually, I have one question, Michael.
Okay.
I'm just wondering how it is possible that the compare function in the Java actually is possible to compare if something is superclass of the type. I just wasn't able to get around this.
Yeah, I understand. So let me find that one again. This sort.
Yeah, this sorting.
Okay, so let's have a example where we have a class hierarchy, like we had like an animal and a dog. Like dog is an animal. Now we have a list of dogs. Okay, we would have a list of dogs. Now let's imagine I have a comparator implementation on an animal, so I can compare two animals, and I pass in that implementation of the comparator that can handle animals, that can return a difference, or like which is first, which is second. Now, when you call the sort method, the implementation of the sort function would, for example, let's use like a bubble sort or whatever, or a quick sort, and it would pass individual elements of the list, which are dogs, to this comparator, which I provided. It can handle animals. And each dog is an animal, right? So that comparator can happily accept the dog, because even though it doesn't know how to access dogs properties, dogs methods and fields, it can access animals properties. So it can, this method with the animal comparator, can sort the dogs based on animal properties. Is that clear?
Yeah, it is. Actually, I was thinking differently about this, but yes.
Yeah. This is the most confusing thing. When you think about contravariance, you always try to imagine a covariant thing. But it's not that you are producing something, you're consuming. And when you're consuming something that is provided to you, it might be a subtype of that. Anything else? If not, or you're not sure how to ask that, just reach me out and I'm happy to discuss. Thank you, everybody, for the attention. I'll see you next time. Yeah.
Thank you. Bye.